In the standard model of our universe, the phases of matter seem entirely settled. We have solids, which act as the structural scaffolding of reality. We have liquids that flow, gases that expand, and plasmas that burn in the hearts of stars. These are the comfortable, observable states of physics that we interact with daily. But deep in the subatomic basement, where the deterministic rules of classical mechanics dissolve into the probabilistic haze of quantum theory, matter is capable of performing a much stranger dance. For decades, condensed matter physicists have theorized the existence of a distinct elusive state, a phase that is not quite a metal, not quite an insulator, and not quite light, but a strange fluid hybrid of all three. It remained a phantom of chalkboard mathematics for 50 years, a holy grail that promised to bridge the gap between matter and pure energy. That search is effectively over. A team at the University of California, Irvine, utilizing the colossal magnetic capabilities of the Los Alamos National Laboratory, has finally trapped this phantom. They call it the Chiral Exciton Liquid. If you were able to hold a droplet of this liquid in your palm, assuming you could survive the cryogenic temperatures and crushing magnetic fields required to sustain it, it would not just sit there like water or mercury. It would emit a coherent, high-frequency glow, a spectral signature of a synchronized quantum dance happening within its very structure. This is not just a new entry for physics textbooks. It represents a potential paradigm shift for the future of electronics, offering a form of computing so robust it could survive the radiation hellscape of deep space without shielding. Today, we are going to deconstruct the physics, the history, and the implications of this discovery. We are going to look at how spinning electron-hole pairs may soon power everything, from Mars rovers to quantum supercomputers. To understand why this liquid is such a monumental discovery, we have to start by breaking down what it is actually made of. You cannot simply pour a chiral exciton liquid from a beaker because it is not made of atoms in the traditional sense. It is made of excitons. In the world of semiconductors, the silicon and germanium materials that power the device you are listening to right now, we typically describe electricity as the flow of electrons. We imagine a stream of negatively charged particles moving through a wire, like water through a pipe. But this is only half the story. When an electron in a semiconductor absorbs energy, perhaps from a photon of light hitting it, it gets excited. It jumps from its lazy, low-energy state in the valence band up to the high-energy conduction band, where it is free to move and conduct electricity. However, nature abhors a vacuum. When that electron leaps up to the conduction band, it leaves behind a vacancy in the crystal lattice where it used to be. In the strange arithmetic of quantum mechanics, this empty spot acts as a distinct entity. It behaves exactly like a particle with a positive charge. We call this a hole. This is where the fundamental romance of the quantum world begins. You have a negatively charged electron that is now free, and it looks back at the positively charged hole it left behind. Through the electrostatic Coulomb force, opposites attract. The electron and the hole are drawn to one another. They begin to orbit each other, spiraling in a tight, bound state, much like a hydrogen atom where an electron orbits a proton. But in this case, there is no proton. There is only the electron and the empty space it left behind, dancing together. This pair acts as a single, neutral quasi-particle. This is the exciton. In normal materials, the life of an exciton is tragic and short. They are incredibly unstable. Eventually, and usually within nanoseconds, the electron loses its energy and falls back into the hole. They recombine, annihilating each other and releasing their stored energy as a flash of light. This is actually the basic principle behind the LEDs in your house. You pump energy in to create excitons, and they die to give you light. Under normal conditions, this life cycle is chaotic. Excitons form, drift randomly like a gas, and then die. They are disordered and fleeting. But physicists have long asked a specific question. What if you could tame them? What if you could cool them down and pack them so tightly together that they didn't act like chaotic individuals, but like a collective? What if they condensed into a liquid, For half a century, this excitant liquid was a major theoretical target. It had been glimpsed in standard semiconductors like silicon at near absolute zero, but those instances were messy, incoherent puddles. The UCI team didn't just want a liquid, they wanted a chiral liquid, and this distinction, the chirality, is what changes everything. The word chiral comes from the Greek word for hand. Your hands are chiral objects. Your left hand is a mirror image of your right, but you cannot superimpose them. No matter how you turn your left hand, it will never look exactly like your right hand. In high-energy physics, chirality refers to the relationship between spin and momentum. If a particle is spinning clockwise as it moves forward, it has one chirality. If it spins counterclockwise, it has the other. In the Chiral Exciton Liquid discovered by the researchers, the excitons are not just randomly bumping into each other, they are locked into a specific direction of rotation. Professor Luis A. Jauregui, who led the study, described it as a fluid-like mixture where electrons and holes rotate in the same direction. This is highly unusual. Typically, if you push matter together, the spins tend to cancel out or randomize. Here, the rotation is preserved and synchronized. Think of the difference between a mosh pit, which is a random guess of people slamming into each other, and a synchronized swimming team, which is a coherent liquid moving in unison. Because they are all spinning the same way, the liquid becomes incredibly robust. It resists disruption. And crucially, when the excitons inevitably recombine and die, they don't just release a random photon. Because their spin was synchronized, the light they emit is coherent and circularly polarized. The liquid doesn't just shine. It broadcasts a structured quantum signal. So how do you actually create this state? You cannot do it in a standard silicon chip. The environment is too noisy, and the quantum interactions are too weak. To birth this state, the researchers needed a material that was already straddling the edge of quantum weirdness. They chose hafnium pentatelluride. This is a layered crystal that looks somewhat like a metallic flake. It belongs to a rare class of materials known as topological insulators. These are materials that are insulators on the inside, meaning they block electricity but are highly conductive on their surface. In these materials, electrons are forced to move in specific lanes defined by their quantum spin, which protects them from scattering. But the material alone wasn't enough. The researchers needed to force the electrons and holes closer together than nature usually allows. They needed a pressure cooker. This brought the team to the National High Magnetic Field Laboratory in Los Alamos, New Mexico. This facility houses magnets capable of generating fields that can literally rip ordinary metals apart. The experiment involved placing a tiny flake of hafnium pentatelluride into the bore of a magnet and cranking it up to 70 teslas. To put 70 teslas in perspective, a strong refrigerator magnet is about 0.01 Tesla. An MRI machine is about 1.5 to 3 Teslas. 70 Teslas is a magnetic field so intense, it distorts the electron orbitals of atoms themselves. As the magnetic field ramped up, the researchers monitored the conductivity of the crystal. They were looking for a signature, a change in how electricity moved through the sample. At low fields, the material behaved normally. But as the dial hit the critical threshold, something dramatic happened. The electrical conductivity plummeted abruptly. The system had shifted into the exotic excitant state. The massive magnetic field had squeezed the electron wave functions. It forced the electrons and holes to pair up tightly, preventing them from flowing as independent electrical current, which is why the conductivity dropped. Instead, they formed the Chiral Exciton Liquid. Under these extreme conditions, the gas of excitons condensed. They aligned their spins. They began to flow as a unified quantum fluid. The result is a state of matter that glows with a coherent, high-frequency light in the terahertz to infrared range. This glow is the scream of the quantum fluid. It is direct evidence that the electrons and holes have not just paired up, but have formed a macroscopic quantum state similar to a Bose-Einstein condensate or a superconductor. Now, why does this matter outside of a high-energy physics lab? Why should we care about a microscopic drop of invisible fluid inside a massive magnet? The answer lies in its resilience. Most quantum states are incredibly fragile. Superconductors break if you warm them up even slightly. Quantum computer qubits decohere, meaning they lose their quantum information if you look at them wrong. They are delicate snowflakes. The Chiral Exciton Liquid, however, appears to be the cockroach of quantum states. It is surprisingly tough. The topological protection granted by the hafnium pentatelluride crystal structure means that the spinning direction of the electrons is locked in. Impurities, dirt, or radiation have a very hard time disrupting the flow, because to stop the flow, you would essentially have to reverse the spin of all the particles at once, a statistically impossible feat. This resilience has led the researchers to propose a killer application: deep space technology. Space is a graveyard for electronics. Outside the protective bubble of Earth's atmosphere and magnetic field, cosmic rays and solar radiation bombard everything. High-energy particles smash through silicon chips, flipping bits, changing a 0 to a 1, or physically destroying the transistors. This is why the processor on the Mars rover is roughly as powerful as a desktop computer from the late 1990s. It has to be old, big, and heavily shielded to survive. A computer based on chiral exciton liquids would function differently. It wouldn't rely on the movement of single electric charges, which are easily knocked off course by radiation. It would rely on the collective spin of the exciton liquid. Because the state is collective, a single cosmic ray hitting the liquid is like throwing a pebble into a rushing river. The river flows on. The information is stored in the macroscopic swirl of the liquid, not on an individual electron. The researchers noted specifically that this newly observed quantum matter is not affected by radiation. This makes it a perfect candidate for the brains of probes sent to Jupiter's intense radiation belts, or generational ships headed for other stars. Beyond space travel, the discovery opens the door to a new class of devices on Earth called spin optoelectronics. Current electronics are charge-based. We push electrons through wires. This generates heat and hits speed limits. Photonics, which uses light, is fast but hard to control. The chiral exciton liquid bridges the gap. It is matter that turns into light with perfect efficiency and spin control. This is particularly relevant for the terahertz gap. This is a frequency range between microwaves and infrared light that we currently struggle to generate efficiently. Terahertz waves are incredibly useful. They can see through clothes and packaging for security purposes, and they can transmit data thousands of times faster than 5G. A chiral exciton liquid could act as the perfect terahertz laser. Furthermore, in the realm of quantum computing, we need to move information from one qubit to another without losing the quantum state. A flowing liquid of chiral excitons could act as a quantum wire, transporting spin information across a chip without the decoherence that plagues metal wires. Because the excitons are neutral, they can move without resistance in certain modes, transporting energy and spin rather than charge, meaning no Joule heating, no wasted energy. Of course, there is a catch. The current limitation is the environment. 70 Teslas is not portable. We cannot launch a magnet the size of a building into space just to run a chip. The next great challenge for the UC Irvine team and the global physics community is to stabilize this state at lower magnetic fields and higher temperatures. However, the history of physics is full of such progressions. MRI machines once required entire buildings. Now they fit in a single room. Superconductors were once stuck at 4 Kelvin. Now we have high temperature variants that work at liquid nitrogen temperatures. The fact that the chiral exciton liquid exists at all proves the physics is sound. The rest is engineering. The discovery of the chiral exciton liquid is a reminder that we have only scratched the surface of what matter can do. For centuries, human innovation was defined by manipulating matter at the macro scale. banging rocks, melting metals, pouring concrete. Then, in the 20th century, we learned to push electrons through silicon, giving birth to the digital age. Now, we are entering an era where we manipulate the collective identity of quantum particles. We are learning to choreograph the spin of electron-hole pairs, forcing them to hold hands and pirouette in a glowing, fluid unison. It is a state of matter that glows with the promise of the future, a light that might one day guide a spacecraft through the dark, radioactive void between the stars, powered by the coherent dance of the quantum deep.